Okay, for this week, I'll introduce you to the central limit theorem, and we'll apply the central limit theorem and use the using what's referred to as the z-test. And the study I'm going to talk about is a study that relates to my backyard chicken coop. And then the picture here, you can see the chickens. This is from years ago, actually. I have a sad story about raccoons and chickens. It's pretty vicious. I don't think it's so I don't want to shock people. Anyways, so that's what today is all about. Okay, so a small chicken farmer. You when you have egg-laying hens, you get them from your local farm store. They used to be referred to as the co-op store. Um, And where you get them from is there's hatcheries throughout Ontario, and the big one for this part of Ontario is in Mennonite country. I forget the name of the little village that it's in. Myra, I can't remember. Um, what you get is you order them, and then at your local co-op store, they'll have what's referred to as Chick Day. And on Chick Day, your little chicks show up at the co-op store in a big cardboard box. You can hear them peeping away, and you pick up your order. You can order as many as you want, but a small backyard chicken coop, probably about maybe 4 or 5. You can also get what are referred to as ready-to-lay hens. And the ready-to-lay hens, they're already raised and ready to lay eggs. So in the marketing brochure for the hatchery, they claim that their hens produce on average 250 eggs per year with a standard deviation of 5 eggs, right? So they're saying, okay, so our chickens are really good, but there's always a variation in terms of the number of eggs that a hen will lay. But population mean is 250, and the population standard deviation is 5 eggs. So I'm going to run a study to assess whether or not the hatchery is working to its standard. Because my concern is, I suspect that the hatchery has changed owners, and now a couple of years in, I think the hatchery business, that business is the work's getting a bit shoddy. The hens that lay the eggs that are hatched, and the incubation, it's not running as efficiently or effectively it has in the past. So I believe that the true population mean is not what they say, 250 eggs per year. I believe it's something less than that. So the hens are gotten weaker, they lay fewer eggs. So I'm going to run a study to test this hypothesis, right? To assess whether or not the hatchery is not working to its standard, right? That the hens on average are laying less than 250 eggs. Okay, so my null hypothesis is the mean number of eggs laid does not differ significantly from the hatchery standard of 250 eggs. So mu equals 250. So the null hypothesis is that they are actually still functioning to their standard, even though I believe that they're not. And the alternate hypothesis is mu less than 250 eggs. Right? So the alternate hypothesis is typically the reason why you're running the study. Right? I'm running the study because I'm concerned that the hatchery is not functioning to its standard, that they're actually laying less than 250 eggs. Okay, so for my study, on the left is the population. That's the hatchery, and that's all the little chicks that are running around. I randomly select 25 hens from that population. It's a representative sample. It is random selection. And over a 1 year period of laying period, I count the number of eggs that each of my 25 hens lays. And for my sample of 25 eggs, on the right-hand table is chicken 1 or hen 1 through 25, and there's the number of eggs that each chicken laid during the year. If I calculate the average of from this sample of 25 hens, the average number of eggs laid is 248. So it's slightly less than the 250. And I still want to run my inferential test to see, is my mean of 208, is that significantly less than the expected mean of 250, if the null hypothesis is true? Okay. The annual number of eggs laid in the population is normally distributed. So the population mean is 250 eggs for the null hypothesis. So here it is. This is the population. So the population is 250 eggs, or average is 250 eggs with a standard deviation of 5. Right? So there's a chance I could get a hen that only lays 233 eggs instead of 250. And it is normally distributed. Okay. Now, as we know from our studies, the chi-square study with the jelly beans, for example, if I'm randomly drawing a sample from this population, this is a frequency distribution, a relative frequency distribution, there is a very slim chance that I could draw 25 hens from the bottom end of that table, or the bottom end of that distribution. So I could get 25 hens where all 25 hens lay somewhere between 235 and maybe 249 eggs, right? That's well below. That could happen. Now, what is the chance of that happening? Well, that right now I don't know, but I'm pretty confident that that would be pretty slim, right? But it still could happen. So this is the null hypothesis. This is the population distribution for if the null hypothesis is true. And I recognize that I could get a sample that is wildly out of whack with what's going on in that population. Now, it is not very likely, as we'll see in a little bit. Okay. Okay, let's stop here for a sec. I'm going to show you what I did. Okay. So, what I did was, this is the program Python. So I used a random number generator with a Gaussian normal distribution, and I created a population of hens. This is just an artificial population, right? I just created one. And I created it so that the mean was 250 eggs, and the standard deviation is 5. And I did that. I created a sample, a population of 200,000 chickens, right? So here is my population. This is run through Python. This is just a theoretical population. The mean is 250 and the standard deviation is 5. And in this population, if I go all the way down to the bottom, this is the hen number, there are 200,000 hens in this population. Okay. Then what I did was, and I calculate, I do the frequency distribution for those 200,000 hens, and this is what the frequency distribution looks like for the number of eggs laid. So one hen out of the 200,000 laid 229 eggs, even though the population mean is 250 and the standard deviation is 5. All the way up to, I had one super layer. She laid 272 eggs out of 250,000 hens. There was only one hen that did that. Now, if I add this up, if I sum that up, it'll add up to 200,000, right? So that's my 200,000 hens. And I just have the relative frequency distribution. So from this population, this is where the frequency distribution was derived from. I go into that, and this is what I did in my little Python program, just as a simulation. So what I did was, I went in there, and in that population, and I randomly sampled 25 hens. So I went into this population here of the 200,000 hens, and I randomly sampled 25 hens. So I drew 25 hens from this population, and then I calculated the sample mean for those 25 hens. I then went back and did this again. I went in and sampled another 25 hens and calculated the sample mean. Right? So what I have is, I have one study with 25 hens, an artificial fake study, and I calculated the sample mean for those 25 hens. I then went in and did that again. I randomly sampled 25 other hens, or 25 hens, it could be the same, and I calculated the sample mean for that sample of 25. So what I did is I resampled from my population samples of 25. So my resample was, and I sampled over and over and over again. So what I did was I ran 200,000 studies. And for each of those 200,000 studies, I sampled 25 hens. And then I calculated the sample mean. So here it is. So the first sample, n is 25, right? So I can make n equals 25. So there's 25. So n is 25. So there were 25 hens in this study, randomly sampled from the population, and the mean for those 25 hens was 250.52. The second study, randomly sample 25 hens and calculate the sample mean. I do this. I sweep through that and do that exercise just as a theoretical exercise. I'm only just doing it because I can mess around in Python. And I did that, and I ended up with 200,000 studies. So I have in here 200,000 random samples of 25 hens from my population. So I essentially ran my study 200,000 times, and for each of those 200,000 times, I had a sample size of 25. Now, the thing that's important, what I want to do is, now that I have that, so I have 200,000 sample means, and I want to figure out the mean and standard deviation of those sample means. The mean from this simulation, the mean of my 200,000 sample means, the mean is 250, which kind of makes sense because the population mean that I drew them from was 250, right? So the distribution here, this distribution of sample means has a mean of 250, which matches the mean for the population from which I drew the samples from. And this is the population I drew the samples from. So, right, a population mean of 250. Now, what's interesting is the standard the standard deviation of those m's, or sample means. So the standard deviation of these 200,000 sample means is 1. It differs from the standard deviation of the population of hens. Like, these are individual hens. This is these are not individual hens. These are samples of 250 or 25 hens. So, and what it means is the standard deviation for this distribution of sample means is a lot less. So here they are. Here's the frequency distribution, relative frequency distribution for my 200,000 hens, or my 200,000 studies, right? So these are 200,000 sample means. Each sample mean has 25 hens in it. And there's what the distribution looks like. It's a lot narrower and more tightly clustered close to the mean of 250 than the population distribution here, right? So here's the population distribution of individual hens. Here's the distribution of sample means. So what this means is, as your sample size kind of like reduces the variation. When I'm focusing on not just one hen, I'm focusing on the collective input of 25 hens, and that's my sample mean. That's what we're going to use, because when I'm going to compare my sample mean of 248 for my sample, my actual sample of 25 hens, I'm going to compare that sample mean of 248 not to the population of individual hens, but to this theoretical population here of a distribution of sample means, where for each sample mean the n is equal to 25. Okay. So I did this through a simulation. Yes? Okay. So I did this through a simulation. Okay. I did this through a simulation, though the beauty of it is I actually don't have to do the simulation, because there is a relationship between this standard deviation and this standard deviation. And that relationship is let's go back to my slide here. So the expected value for the distribution of sample means is equal to the, and it's referred to as the expected value. So that the mean for the distribution of sample means mu m is equal to the mean for from the population of the individuals mu. So right here is the mean for the population of individuals. This is the mean for that 200,000 sample means. Right? Makes sense. The central limit theorem is the standard deviation for the distribution of sample means, which is referred to as a standard error, is equal to the standard deviation from the population of individuals divided by the square root of my sample size. So in my study, so if I look at this, the population standard deviation is 5. My sample size is 25. 5 over the square root of 25 is 1. So my simulation matches what the central limit theorem tells me. And with the central limit theorem, I don't actually have to run a simulation. All I have to do is apply this formula or this theorem. So as long as I know the population standard deviation and I know my sample size, I can calculate the standard deviation for the distribution of sample means. Okay. So this is, just to review, this is the distribution of individual hens. Population mean of 250, population standard deviation of 5. This is the distribution of sample means through application of the central limit theorem. The mean or expected value for the distribution of sample means, mu m, is equal to 250, the population mean from the individual hens. The standard error, or the standard deviation for that distribution of sample means, is equal to sigma, the population standard deviation, over the square root of n, my sample size, which in this case is 5 over the square root of 25. If you can get this theorem, you're in great shape for the rest of this course. Okay. Now I want to see, is my sample mean of 248, how unlikely is it to have occurred in a distribution where the mean is 250 for the distribution of sample means and the standard deviation is 1? I use the z-test. I go to my go-to curve, the standard normal curve. So 248 minus 250 divided by 1 is equal to minus 2. Then I can go and look up in the standard normal curve, what's the likelihood of getting a sample mean less than 248? And that's kind of my metric. So the probability of getting a sample mean, I'm using the standard normal curve, the probability of getting a sample mean less than 248 is 0.0228. So if the null hypothesis is actually true, and if I were to run this study 200,000 times, less than 2.28% of those sample means would be less than my sample mean of 248. Since the probability of getting a sample mean less than 248 is 2.28%, that's less than my 5% cutoff, right? So my alpha is 0.05. So because the likelihood of getting a sample mean of 248, or getting a sample mean less than 248 is 0.0228 or 2.228%, and because that's less than 0.05 or 5%, I reject the null hypothesis and I conclude that that hatchery is not working to its standard. And null hypothesis does not differ from 250. Alternate hypothesis, the population mean is actually less than 250. So my result is the mean number of eggs laid per year for my sample of hens collected for the study, a mean of 248 eggs per year with a standard deviation of 5. Differed significantly from the assumed population, mu equal to 250, sigma equal to 5. My z for my study was minus 2, p equal to 0.0228, which is less than 0.05. The result suggests that the hatchery is producing hens that on average lay less than 250 eggs per year. Now that 0.0228 is referred to as a type 1 error. There is a chance that I could have got that sample, right? So I could have got that sample if this had happened. If I just drew a lot of hens from the bottom end of that curve. It's highly unlikely, and it's below my threshold of 5%. So the unlikelihood of that is what drives me to reject the null hypothesis and take that risk of committing a type 1 error. Okay, and the last part is a practice question. Give that a shot, and we'll take it up in class, and I'll post a video on it.